In the series Advanced Mathematics, we are going to start now lecture 7 of chapter Vector Calculus, and in this lecture we will talk about the Green's theorem. So first we look at the statement over here. We are saying we have the functions phi x and psi x such that the derivatives, these functions, these are continuous, and the derivative of phi with respect to y and derivative of psi with respect to x, they are continuous in the region E of xy plane bounded by the closed curve C. Then the theorem states that the closed integral over C of phi dx plus psi dy, that is equal to double integration over E curly psi by curly x minus curly phi by curly y into dx dy. So we are considering the region E. It is bounded by closed curve C such that any line parallel to any axis cuts C into at most 2 points. So we are saying that E is bounded by x is equal to a, this thing is shown in the figure, x is equal to b. Then we are having these two curves, y is equal to y1, we are saying this is the curve C1, and y is equal to y2, this is the curve C2. This is one case we are considering. So what we have is the double integral curly phi by curly y into dx dy. The value we have, this is equal to double integral y1 of x to y2 of x curly phi by curly y into dy into dx, and the limits for x we have, they are varying from a to b, and on solving this we obtain this is equal to integration a to b phi of x comma y2x minus phi of x comma y1x into dx. So this is equal to minus integration, we are saying a to b, it is integration over c2, it is phi of xy into dx minus integration over c1, it is a phi of x comma y into dx. So this value is equal to minus of integration over c phi of dx. Similarly, if we calculate the value of double integral curly psi by curly x into dx dy, now we are considering that y is equal to c. The region we are considering, it is bounded by y is equal to c to y is equal to d, and the curve c1 we have, it is x is equal to x1y, and curve c2 is x is equal to x2y. Now if we calculate the value of this term, the answer we obtain, this is equal to integration over c psi dy. These calculations, these are similar to that we have done in the previous case. So what we obtain is, if we add both these equations, we obtain integration over c, it is phi dx plus psi dy, that is equal to double integral over e curly psi by curly x minus curly psi by curly y into dx dy, and this is what the Green's theorem states. If we extend this result to any region E by dividing it into a finite number of such regions, such that the boundary of each is cut at most into 2 points by lines parallel to the axis, and applying these results to each of these subregions and adding the results, the surface integral combined into an integral over the whole region E. So we are saying, suppose we are talking about this is the region E, we have divided it into these parts. We are saying when we calculate, this is the region E1, then we have E2, then we have E3, so on, continuing like this, we have it as En. We are saying the integral we calculate for this E1, this boundary is being calculated. Then for this E2, when we calculate for this E2, this boundary is being calculated. When we add both these values, the net result will become 0. Similarly, for these common boundaries, the result will become 0. And what we will be left with is only the outer region over here. This outer region we are left with. So we are saying the line integrals over the common boundaries cancel each other, and each is covered twice but in opposite direction. So the remaining line integral combines into one line integral over the boundary of the curve C. So these internal regions, we are saying, once it is being counted in this direction, then it is being counted in this direction. So sum of both of these, this inside part we are talking about, the value becomes 0. So what we are left with is, the integral about the boundary. Now next we have the problems based upon Green's theorem. So the first question we have is, we have to verify the Green's theorem for the region for this integral, and where C is the boundary of y is equal to x and y is equal to x square. So y is equal to x is a line and y is equal to x square is a parabola. So this region is shown over here. We are saying this is the line y is equal to x, and this is the parabola y is equal to x square. So their point of intersection, that will be 1, 1 and 0, 0. We are talking about this region. So we are having two curves over here. We are saying this is the curve C1, and this line, it is the curve C2. So to verify the results, we are first calculating the value of integration over C xy plus y square times dx plus x square times dy. So we are calculating this integral over the curve C1 and C2. So this becomes integration over C1 xy plus y square dx plus x square dy, and integration over C2, it is xy plus y square times dx plus x square times dy. Now if we look at both these curves, we are saying when we are talking about the curve C1, the equation of this curve, that is y is equal to x square. So we have dy is equal to 2x dx. So in place of y we are writing x square. So for this curve C1 we obtain x is varying from 0 to 1. This becomes x cube plus x raised to the power 4 into 2x. This is dx over here, so it will remain as it is. Plus it is x square. In place of dy we are writing it is 2x dx. So this whole value, this will become equal to integration 0 to 1. The values we obtain, it is 3 times x cube plus x raised to the power 4 into dx. And these two values we have, it is integration for this curve. We have y is equal to x, that is dy is equal to dx. So we are writing it is integration 0 to 1. The value will become x square plus x square into dx plus x square into dx. This whole value will become integration 0 to 1, 3x square dx. Now if we add both these terms, we are having, this is one integral, this is the second integral. When we add both these values, we obtain the final integral in this form. And integrating this term, the answer we obtain, that is equal to minus 1 by 20. The answer we obtain, it is minus 1 by 20. So next we are saying, let phi is equal to xy plus y square. We are saying phi is equal to xy plus y square, and the value of psi is equal to x square. So these two values we have obtained from the given integral. Now if we calculate the value of curly psi by curly x minus curly phi by curly y, the answer we get, it is 2x minus 2y. So it is equal to x minus 2y. Now we have to verify the Green's theorem. So we are evaluating the value of double integral over E x minus 2y into dx dy. So this is equal to double integral x minus 2y dy dx. Now if we look at the region again, we are talking about, we have this curve like this, we have this curve like this. Now y is being varying, So y is varying in this direction. So we are saying y is varying from this point to this point. At this point, the value of y we have it is equal to x square. This value we have it is x square, and it is varying up to x, and the value of x it is varying from 0 to 1. The value of x it is varying from 0 to 1. Now in integrating this value, we obtain this is equal to integration 0 to 1 xy minus 2y square, limits are x square to x. Answer we obtain it is integration 0 to 1 x square minus x cube plus x4 into dx. We are writing this is equal to integration 0 to 1 x raised to the power 4 minus x raised to the power 3 into dx. So answer we obtain it is x raised to power 5 by 5. Limits when we substitute we get 1 by 5 minus 1 by 4, that is equal to minus 1 by 20. So we are saying the answer obtained from this it is minus 1 by 20. The answer obtained from the previous integral it is minus 1 by 20, and hence the Green's theorem is being verified. Now next we have is apply the Green's theorem to evaluate this integral where C is the boundary of the area enclosed by x-axis and upper half of the circle x square plus y square is equal to a. So this is the region shown over here. So the value of phi we have it is 2x square minus y square. The value of psi we have it is x square plus y square. So by using the Green's theorem we obtain this is equal to double integral. The region we have it is x square plus y square is equal to a, and y is greater than equal to 0, upper half. So y is greater than equal to 0, and the values we will have over here it is del psi by del x. So del psi by del x it is 2x plus, and the second value we will have it is del phi by del y, so it is 2y. So this is the value we are calculating, del psi by del y, that is equal to minus 2y, del psi by del x is equal to 2x. Subtracting these values we are getting this answer, and the limits that we have over here it is the value we have over here it is dx into dy. So we are writing the answer by making the substitution. X is equal to r cos theta, y is equal to r sin theta. This integral will become double integral 2 into the value of r will come out, it is cos theta plus sin theta. In place of dx dy we will have it is r dr d theta, and the limits they will vary from 0 to a and 0 to pi. 0 to pi because it is the semicircle. Over here the value of theta that is 0, and over here the value of theta it is pi. So on integrating this value the answer we obtain it is equal to integration 0 to pi, it is cos theta plus sin theta into d theta, and integration 0 to a 2r square dr. So the answer we get it is sin theta minus cos theta. Limits are varying from 0 to pi. Then it is 2 by 3r cube. Limits are varying from 0 to a. So the final answer we get it is minus 1 into 2 by 3a cube. That is equal to 4 by 3a cube. So we are saying the value of this integral it is 4 by 3a cube. Next we have is using Green's theorem in the plane, we have to evaluate the value of this term for a closed curve C given by x square plus y square is equal to 1 and z is equal to 0. So this integral we can write it is integration over C cos y dx plus x into 1 minus sin y into dy. We are writing this is equal to double integral. The derivative of this term with respect to y, that will be minus sin y, and derivative of this term with respect to x it is minus 1 minus sin y into dx dy, and the region we have it is x square plus y square is equal to 1. So on solving this we are saying this is double integral dx dy, this sin y gets cancelled, it is x square plus y square is equal to 1. So we are saying this is area of circle x square plus y square is equal to 1. So that is equal to pi r square, that is equal to pi. So we are saying the value of this integral, it is equal to pi. Next is evaluate by Green's theorem. This integral we have to evaluate, where C is the rectangle with the vertices this. So again, if we apply the Green's theorem over here, we are saying it is double integral. The terms we have, it is e raised to the power minus x sin y and e raised to the power minus x cos y. If we take the derivative over here, we get it is e raised to the power minus x into, we have over here it is minus this into cos y minus e raised to power minus x into cos y into dy dx, and the region, it is bounded by these curves. So what we have over here, it is integration minus 2 common. We are left with this e raised to the power minus x cos y dy dx. Now look at these terms over here. We are saying this is a rectangle, this point it is 0. So x, it is varying from the point 0 to pi, x is varying from 0 to pi, and y is varying from 0 to pi by 2, y is varying from 0 to pi by 2. So these are the limits in this case. So these are the limits we have substituted over here. Now on evaluating these values, the answer we obtain, this is minus 2 integration 0 to pi by 2 cos y dy integration 0 to pi e raised to the power minus x dx. So this is equal to 2 into e raised to the power minus x, limit is 0 to pi, then sin y limit is 0 to pi by 2. So this is equal to 2 into e raised to the power minus pi minus 1. So this is the answer we obtain corresponding to this integral. This line integral we have calculated using the Green's theorem, and we obtain the final answer as 2 into e raised to the power minus pi minus 1. Now next question we have is evaluate this integral by Green's theorem, where this c is the cardioid, r is equal to a into 1 plus cos theta. So if we use the Green's theorem over here, this integral will become double integration. It is partial derivative, this term partial derivative with respect to x, and this term partial derivative with respect to y. So we obtain the answer as y square plus x square into dx dy. Now the equation of cardioid that is given in the polar form, it is r is equal to a into 1 plus cos theta. This integral is over this region. So we are changing this integral to the polar form. We are substituting x is equal to r cos theta, y is equal to r sin theta. So this integral becomes double integration. This value becomes r square. In place of dx dy we have it is r dr d theta, and the limits we have, the limits for r we have it is varying from, if we draw a line over here, r is varying from 0 to a into 1 plus cos theta, and then the value of theta, it is varying from, over here the value of theta is 0, and then when it is moving this complete cardioid we have, so it is from 0 to 2 pi. So if we integrate this value, this integration, this will become r raised to the power 4 by 4. So we obtain it is a raised to the power 4 by 4 integration 0 to 2 pi, the value we have it is 1 plus cos theta raised to the power 4 into d theta. Now on solving this we will obtain it is a raised to the power 4 by 4 integration 0 to 2 pi, this value we are writing it is 16 cos 8 theta by 4 into d theta. Now if we substitute theta by 2 is equal to phi, we get d theta is equal to 2 d phi. So this integral will become equal to, this integration will become equal to 8 a raised to the power 4 integration 0 to pi cos 8 phi d phi, and it is 0 to pi over here. If we change it to 0 to pi by 2, this 8 will become 16, and the answer we get it is 16a raised to the power 4 into this power over here, it is 8, so we get it is 7 into 5 into 3 into 1. We are using the reduction formula over here. It is 8 into 6 into 4 into 2 into pi by 2. So the answer we get, that is equal to 35 by 16 pi a raised to the power 4. So we are saying the value of this integral, it is 35 by 16 pi a raised to the power 4. Next is verify the Green's theorem. This integral is given where C is the boundary enclosed by the curve y is equal to root x and y is equal to x square. So we are talking about two parabolas. One is y is equal to square root of x, and second we have it is y is equal to x square. So first of all, we are integrating this term. We have, this is, say this is the curve C1, we are saying this is the curve C2. So over the curve C1 we are having this integral, plus over the curve C2 we are having this integral. Now we are saying for the curve C1, we have y is equal to x square, dy is equal to 2x dx, and for the curve C2 we have the value x is equal to y square. So we are writing dx is equal to 2y dy. So if we substitute these values in these integrals corresponding to this first one, the integral will become integration over, we are changing the value of y to x, and the limits of x we have, they are varying from 0 to 1. In place of y we are writing x square, so we are having 3x square minus 8x raised to the power 4 into dx plus 4 into x square minus 6x cube, and in place of dy we have it is 2x dx. Now for this second integral, for this C2, we are having the limits of y, they are varying from 0 to 1 to 0. We are saying the limits of y, they are varying from 1 to 0 because this curve C2 is moving in this direction. So at this point the value of y, it is 1, and at this point this is 0, we are moving in this direction. So we substitute x is equal to y square over here. So we get it is 3y raised to the power 4 minus 8y square into 2y dy plus we have 4y minus 6y cube into dy. So we have obtained this integral, and on solving this integral, these calculations, these are shown over here, we obtain the final answer as 3 by 2. So this is the value of this integral. Now we use the Green's theorem to prove that by Green's theorems we are also obtaining the similar result. So this is the function given to us. This is the function given. We have to take the partial derivative with respect to x of this term, partial derivative with respect to y for this term. So we are writing this is equal to double integral over the region E, and the partial derivative with respect to x, it is minus 6x, and partial derivative with respect to y, it is minus 6y, and partial derivative it is plus 16y into dx dy. So we are writing this is equal to double integration 10y dy dx. Now the limits for y, now the two functions that we have, they are in this form. So we are saying y is varying from these, between these 2 points. So it is varying from x square to square root of x, and x is varying from 0 to 1. Now when we integrate this value, we obtain this is 5 times integration 0 to 1. When you integrate this value and substitute these limits, you will get x minus x raised to the power 4 into dx. So this is equal to 5 into x square by 2 minus x raised to the power 5, limit is 0 to 1. So answer we get it is 5 by 2 minus 1, that is equal to 3 by 2. So we are saying in both the cases we obtain the same answer, hence the Green's theorem is verified for this case. Now next is evaluate this integral over the region C, where C is the boundary of the region in the first quadrant, that is bounded by the curve y square is equal to x and x square is equal to y. So these are the curves shown over here. We are saying we have x square is equal to y and y square is equal to x. If we find the point of intersection, we are getting x square is equal to, if we substitute the value of y over here, we are getting it is equal to x. So we are getting x is equal to 0 and 1. So these are the 2 points we have, 0, 0 and 1, 1. We have to evaluate this integral. So we are using the Green's theorem over here. So this integral becomes a double integral. The partial derivative of this term with respect to x it is 2. Partial derivative of this term with respect to y it is minus 2y, and the minus sign is there. So we are getting minus 2y. Then it is dy dx. Now the limits for y they are varying from, if we look over here, the limits for y they are varying from this curve it is y is equal to x square, and on this curve y is equal to square root of x, and the value of x it is varying from 0 to 1. So if we integrate these values, we get it is integration 0 to 1. On integrating this, we get it is 2y minus 2y square by 2. If we substitute these limits, the answer we obtain it is 2 root x minus 2x square plus x raised to the power 4 into dx, and we are writing this value is equal to, again when we integrate this value, we get it is 4 by 3 x raised to the power 3 by 2 minus x square by 2 minus 2 by 3 x cube plus 1 by 5 x raised to the power 5. This is equal to, and the limits we are substituting over here, they are varying from 0 to 1. When we substitute limit 0, the value becomes 0. When we substitute limit 1, we get it is 4 by 3 minus 1 by 2 minus 2 by 3 plus 1 by 5, and on solving this, the answer we obtain it is 11 by 30. So the value of this integral we obtain it is 11 by 30. Next is find the work done by the force this in moving the particle along the path C containing the curve x plus y is equal to 0, x square plus y square is equal to 16, y is equal to x in the first and fourth quadrants. So these are the curves we have drawn over here. We are saying x square plus y square is equal to 16, this is the circle. Then we have the line x plus y is equal to 0, that is x is equal to minus y. Then we have the line y is equal to x, that is x is equal to y. So we are talking about this portion. Now in this portion we have to evaluate this, the line integral of this. We are saying it is integration f vector dot dr vector. This is the work done in this region, and by Green's theorem we have this value is equal to double integral, the partial derivative of this with respect to x it is 1, and this is minus 3y square, so it becomes plus, so it is 1 plus 3y square into dx dy, and this is the region of integration we are saying. Now if we convert it to polar coordinates, we are substituting x is equal to r cos theta, y is equal to r sin theta. So this integral will become double integration 1 plus 3 r square sin square theta into r dr d theta. Now the value of r that is varying over here, it is varying from the point 0 up to the point, this is 16, so it is varying up to 4, and the angle theta it is varying from minus pi by 4 to pi by 4. Minus pi by 4 is corresponding to this line, this is corresponding to theta is equal to minus pi by 4, and this is the line corresponding to theta is equal to pi by 4. So these are the limits in this case. So if we integrate these values, the answer we obtain this is equal to, it is integration 0 to pi by 4 d theta, and it becomes 2 times over here. Then it is integration 0 to 4 r dr plus 3 integration 0 to pi by 4 1 minus cos theta d theta, and integration 0 to 4 r cube dr. Now if we integrate these terms, we are having the integration of this term, this will be r square by 2. On substituting the limits, we will obtain the answer. It is 2 into pi by 4 into 1 by 2 into 4 square. Then next value we will have, it is plus 3 into this integration, it is theta minus 1 by 2 sine 2 theta, limit 0 to pi by 4, and then next value we have, it is 1 by 4, the limit when you substitute it is 4 raised to the power 4. So on solving this you will get, it is 4 pi plus 3 into pi by 4 minus 1 by 2 into 64, and this value comes out to be equal to this. On solving this value we obtain the final answer is equal to 52 pi minus 96. So the integral, that work done in this case, it is 52 pi minus 96. Now next question we have is, verify the Green's theorem in the plane. This function is given where C is the boundary of the annulus enclosed by the circle x square plus y square is equal to 1, x square plus y square is equal to 9. So these are the two circles that we have. This is the circle we are having, x square plus y square is equal to 1, and this is the circle we have, x square plus y square is equal to 9. Now first of all we have to integrate on the surfaces. It is boundary of the annulus enclosed by these two circles. So if we are saying this is the curve C1 and this inside curve we are saying it is the curve C2, and we are integrating this value, then this integral will become integration over the curve C1, it is 2x minus y cube dx minus xy dy over C1 plus integration over C2. Now if we look at these two curves, we are saying on the curve C1 we substitute x is equal to 3 cos theta, y is equal to 3 sin theta, the radius is 3 over there. So the value of dx we obtain, that is equal to minus 3 sin theta, the value of dy we obtain, it is 3 cos theta, and theta is varying from 0 to 2 pi. Similarly for this curve C2 we are substituting x is equal to cos theta, y is equal to sin theta, and the value of dx dy we have, dx is minus sin theta and dy we have, it is cos theta. So both these integrals, on substituting these values, both these integrals, they change to the form, it is integration, theta is varying in both the cases from 0 to 2 pi. In the first case we are getting, it is 6 cos theta minus 27 sin cube theta d theta, it is dx. So in place of dx we have, it is minus 3 sin theta d theta, then it is minus 9 sin theta cos theta into 3 cos theta d theta. Then next value we have, it is minus integration 0 to 2 pi, we have, it is 2 cos theta minus sin cube theta into minus sin theta d theta, then it is minus sin theta cos theta into cos theta d theta. Now if you solve these integrals, when you solve these integrals, and these values, these are shown over here, these are the integrals we have obtained. Now if you solve these integrals, the answer you will get on solving this integral, the answer you will get, it is, and the final answer you will get, it is, this is the value we are talking about, it is 60 times pi. Now in the second case we are using the Green's theorem to evaluate this integral. So this integral we have, so this changes to the form, it is double integration, the partial derivative with respect to x, it is minus y, and partial derivative with respect to y, it is 3y square, so it is with minus sign, so this becomes 3y square minus y into dx dy. Now again changing it to the polar coordinates, it is over the region bounded between the two circles. So if we substitute x is equal to r cos theta and y is equal to r sin theta, we are getting, it is 3 r square sin square theta minus 3 sin theta into r dr d theta. Now the value of r, it is varying from 1 to 3. We are saying this internal radius we have, it is 1, this external radius we have, it is 3, and the value of theta, it is varying from 0 to 2 pi. The value of theta, it is varying from 0 to 2 pi. Now if we solve this integral, the answers we obtain, it is integration 0 to 2 pi. Look at these values over here. We get it is 1 minus cos 2 theta by 2 into d theta, integration 1 to 3 r square dr, then it is minus integration 0 to 2 pi sin theta d theta, then integration 1 to 3 r square dr. Now when you solve these values, when you evaluate these values, the answer you will get, it is 1 by 2 into, when you substitute the limits over here, it is theta minus 1 by 2 sin 2 theta, the limit is 0 to 2 pi, then it is 3 by 4 r raised to the power 4, limit is 1 to 3, then integration of this term, it is cos theta, limit is 0 to 2 pi, then it is 1 by 3 r cube, limit is 1 to 3, and on solving this value, on evaluating this result, the answer you will obtain, it is 60 pi. So we are saying in both these cases, the final answer we obtain, it is equal to 60 pi. Hence we are saying the Green's theorem is verified.